Hello. Having discussed the process of radioactivity in the last class, we are now ready to talk about nuclear energy. Well, all of you now know that energy and mass are equivalent. There is an equivalent relation between energy and mass. And what is that relation? We have E equal to mc squared. And therefore, any discussion on nuclear energy must relate these two, mass and energy. Now, what is the unit for measuring mass? In the ordinary world, when we can all see and measure things easily, we use kilogram to measure mass. But when you want to measure the mass of subatomic particles, we will use a much smaller unit. It is called the atomic mass unit, AMU, or simply, very often, we will call it the unit. Now, what is an atomic mass unit? There is a big history behind it, but we don't have time to go into that history. But I can say the present understanding of an atomic mass unit is 1/12 of the mass of a normal carbon atom. Carbon-12 is the standard. So 1/12 of the mass of carbon-12 is considered to be 1 unit of mass at the subatomic level. In fact, this is the same as 1 gram divided by the Avogadro number. What's Avogadro's number? The number of molecules in 1 mole, or number of atoms in 1, well, that will be 6.03 times 10 to the power of 23. So 1 gram divided by 6.03 times 10 to the power of 23, you can do that approximately. That will work out to 1.66 times 10 to the negative 27 kilogram. If you work out this, that will give you in gram, 1 gram divided by this. And that will give you approximately 1 atomic mass unit is 1.66 times 10 to the negative 27 kilogram. Well, that will be the unit for measuring mass. What is the unit for measuring energy? We have already seen that. Energy is measured in a unit called electron volt. What is an electron volt? It is the energy acquired by an electron when accelerated by a potential difference of 1 volt. Now, what is its value? It will be 1.602 times 10 to the negative 19 joules. So 1 electron volt is 1.602 times 10 to the negative 19 joules. Well, we have now unit for measuring energy, unit for measuring mass, and there is a relation connecting the two. So we are ready to talk about nuclear energy. In the scale of atomic mass unit, the mass of a proton is 1.0073 unit. How about that of a neutron? Is the mass of a neutron the same as that of a proton? Well, the mass of a neutron is 1.0087 unit. Why? What's the difference? Why are these two masses different? Well, we have seen in radioactivity that a neutron can degenerate into a proton and an electron. So the mass of a neutron is actually greater than the mass of a proton. Well, the reason is much more complicated than the one I just said. The mass of an electron is 0.0005486 of an atomic mass unit. Well, If you add these two, therefore, if you add the mass of a proton and the mass of an electron, will you therefore get the mass of a neutron? Actually not. So the explanation of why the mass of a neutron is greater than that of a proton is rather a complicated one. We will not go into the details there. Now carbon-12 is the standard, as I told you, has a mass of 12 atomic mass units. By definition, an atomic mass unit is 1/12 of the mass of carbon-12. It has 6 protons and 6 neutrons. So let's calculate the total mass of these. The total mass of 6 protons, if you multiply 6 by the mass of a proton, you will get 12.096 units. How about the mass of how about the mass of 6 neutrons? Well, what I did is I calculated the mass of 6 protons and the mass of 6 neutrons, which came to 12.096. Well, is that a mystery? You know that carbon-12 consists of 6 protons and 6 neutrons, and the total mass of carbon-12 is 12 atomic mass units. But you take these particles separately and find their mass, the total mass is 12.096 atomic mass units. What does it mean? It means when you bring these particles together to form the nucleus of carbon, some mass seems to disappear. We lose a part of the mass of these particles. So when a nucleus is formed by combining several particles, some mass is lost. Now, how can some mass get lost? Well, how about the conservation of mass and conservation of energy? Now, the lost mass is actually called mass defect. So what is mass defect? When several nuclear particles are brought together to form a nucleus, the total mass of the particles the total mass of the nucleus seem to be less than the total mass of the individual particles. And that mass difference, or the apparent mass lost, is called the mass defect. And actually that mass is not lost, because there is an equivalency between mass and energy, E equal to mc squared. That becomes energy, and that energy is what holds the nucleus together. Well, that's an important concept. So the energy that holds the nuclear particles together is called the binding energy. And where does that energy come from? It comes from the equivalent energy of the mass lost, or the mass defect contributes to the binding energy. When nuclear particles escape the nucleus, well, if nuclear particles are taken out, then a part of this binding energy must also come out. And that is actually the origin of gamma radiation. We discussed in the last class that when an alpha particle is emitted by a nucleus, it is very often accompanied by a gamma radiation. Why? Because alpha particle means a part of the nucleus is torn apart. So the energy that binds those particles within that nucleus has to be released when the particle is broken open or broken away from the nucleus. And that is the origin of gamma radiation. If a massive nucleus splits into 2 pieces, now that's a different story altogether. If a massive nucleus can be made to split into 2 pieces, then the energy holding the pieces together, the binding energy, can be released. So one way to obtain a large amount of energy is to make a large nucleus split into 2 pieces. The total mass of the pieces is less than the mass of the original nucleus. And that difference in the mass defect, is converted to energy according to Einstein's mass-energy relationship, E equal to mc squared. So the binding energy of the nucleus of any isotope can be calculated from the mass defect of the nucleus. Well, we will not be doing all those things. I'm going to condense the whole chapter on nuclear energy into this 1-hour lecture. So you can imagine how much we can actually do. Now, the binding energy per nucleon is an important indicator of the stability of the nucleus. Higher is the binding energy per nucleon, more stable that particular nucleus is. Now here I have a picture of binding energy per nucleon, and binding energy is given in millions of electron volts. Now you must get used to electron volt. Iron, for example, is a very stable element. The nucleus of iron is very stable. Now, the binding energy per nucleon is about 8.8 million mega electron volts. Now, as you go to the left of iron and to the right of iron, binding energy per nucleon decreases. That means they are less stable. So, what happens if an element over here, a very heavy element, splits into two pieces? Sometimes they do that in order to achieve stability. When they do that, the product may be more stable because the products may be more in this region. So, the greatest binding energy per nucleon occurs near the mass number 56, which is that of iron, and decreases both for elements to the left and to the right of that nucleus. Now, more massive nucleus can gain stability. Nuclei in this region can gain stability by splitting into smaller nuclei, releasing their binding energy. Now, a converse effect can also happen. Small nuclei here can combine, releasing their energy, and that will be the process of nuclear fusion. And when splitting occurs, that is the process of nuclear fission. So both these, fusion and fission, is actually the process of releasing the binding energy. When small nuclei come or fuse together to form bigger nuclei, the binding energy, equivalent energy, is released. When very heavy nuclei on the right split into smaller pieces, again the binding energy is converted to energy. Well, if you look at these two lines, the slope of this line is much larger than the slope of this line. What that means is the energy released during fusion process is much greater than the energy released during fission process. Well, let's talk about nuclear fission, which is the most prominent source of nuclear energy at the moment. So that is more important for us. What is nuclear fission? Fission is the process of splitting. So the process of splitting a massive nucleus into more stable, less massive nuclei with the result of releasing energy is called nuclear fission. Now here I have illustrated a fission process. A uranium-235 nucleus, by any chance, if it absorbs a neutron, you see, a neutron going into a uranium-235 nucleus will create great instability. And immediately that nucleus will split into two pieces. And one piece will be rubidium of mass number 90, and the other could be cesium of mass number 143. And in that process, also some free neutrons are released. Now, we will be talking about this as we go on. Now, if you look at that animation, a neutron goes into the nucleus of uranium-235, splitting into two pieces. Now, not always these may not be always the two pieces. We will see another scenario later on. So this is the simple process of nuclear fission of uranium-235 nucleus. Uranium-235 is called a fissionable material. It is capable of undergoing fission after absorbing a neutron. So fission can occur when the nucleus of a heavy atom captures a neutron. In addition to energy, free neutrons are also released during the fission. Very important, because in order that fission may occur, you need free neutrons that can be captured by nuclei. So if one nucleus of uranium-235 undergoes fission by capturing a stray neutron, that fission will release more neutrons which can then be captured by other nuclei to produce fission. So that concept is very important. So if a neutron is captured by a fissionable nucleus, it splits into two pieces. We call them fission products. And also are released free neutrons. On an average, sometimes 2 neutrons, sometimes 3 neutrons. We would say on an average 3 neutrons are released per fission. Now, materials that undergo fission are called fissionable materials. Now, what are some of the fissionable materials that exist in nature? Well, there aren't very many fissionable materials that exist in nature. Some can be made. Well, uranium-235 is actually a naturally occurring isotope of uranium. Now, remember, most of uranium is, the naturally occurring uranium is uranium-238. Uranium-235 is only a very, very tiny part of naturally occurring uranium. Another isotope of uranium is uranium-233, that is a fissionable isotope. And a third fissionable material is plutonium-239. It doesn't really occur naturally, but it can be produced by making uranium-238 radioactive. We will talk about that as we go on. So, 3 important fissionable materials are uranium-235, uranium-233, and plutonium-239. Now, the fission of uranium-235 in reactors is triggered by the absorption of a low-energy neutron. So, the fission is started. In order to start fission, you need low energy, or sometimes they're called thermal neutrons. You need to make those neutrons available to start fission. On an average, as we said, 3 neutrons are released per fission. Now let's look at the fission of uranium-235. Uranium-235 is the chief fissionable isotope used in reactors. Well, in order to produce atomic energy, we build reactors. What is a reactor? We will talk about that later. A reactor is a controlled environment where fission is allowed to proceed, that can be controlled so that energy can be produced and used. Now, here we have an animation. Watch it carefully. A slow neutron is being absorbed by uranium-235. Now, great instability, and there is the product. The product is krypton of atomic mass 92 and barium of atomic mass 142, and also free neutrons. Watch that again. Stray neutron absorbed by uranium-235. Fission occurs, fission products, krypton 92, barium 142, and free neutrons. You see only 2 free neutrons there. Well, in most cases that may be true, but in some cases there may be 3 free neutrons. So this is the process of the fission of uranium-235. Okay. So the fission products are barium, krypton, 3 free neutrons, and of course energy. Now, how much energy? Approximately 200 million electron volts, which is 200 times, well, when I said this is not million, this is million electron volts. Million is the uppercase M. So 200 million electron volt will be 200 times 10 to the power 6 times 1.609 times 10 to the negative 19, and that will work out to 3.22 times 10 to the negative 11 joules for one fission. I hope you followed that calculation. Now what I did here is, instead of writing 1 electron volt as 1.609 times 10 to the negative 19 joules, I wrote 1 million electron volt. This is the equivalent of 1 million electron volt. In other words, 19 minus 6. So 200 million electron volt is 200 times this, which is 3.22 times 10 to the negative 11 joules. Now, that is the energy released per one fission of one uranium-235 nucleus. Now, so if you take 1 gram of uranium-235, how much energy will be released? Can you calculate that? Now, I'm sure you know how many atoms are there in 1 gram of uranium. Well, let's do that. How much energy is released when 1 gram of uranium-235 undergoes fission? The mass of 1 mole of uranium-235 is 235 grams. That's the definition of a mole. So 1 mole of uranium-235 contains 235 grams. That means 1 gram is 1 over 235 of a mole. So the number of moles in 1 gram is 1 over 235. Now, how many atoms are there in 1 mole of uranium-235? That's the Avogadro number. So 1 gram, or 1 mole of uranium-235 contains 6.02 times 10 to the 23 atoms. Therefore, how many atoms are there in 1 gram? That will be 1 over 235 multiplied by the number of atoms in 1 mole, that is the Avogadro number, and that will be 2.56 times 10 to the 21. That is the number of atoms. 2.56 to the times 10 to the power of 21 is the number of atoms in 1 gram of uranium. And each gram of uranium, well, each nucleus of uranium undergoing fission will release this much of energy, 3.22 times 10 to the negative 11 joules. So the total energy released will be the energy released per fission times the total number of nuclei in 1 gram. Total number of atoms is the same as the total number of nuclei. And that is 8.24 times 10 to the power of 10 joules. Now, this is a tremendous amount of energy. Can you calculate how many kilograms of water can be boiled using this energy? Knowing that the amount of energy released, absorbed by water in boiling will be mass times specific heat times the change in temperature. You can do a rough calculation and see how many kilograms of water can be boiled. Now, nearly 250,000 kilograms of water can be boiled using that much of energy. So if you allow 1 gram of uranium-235 to undergo nuclear fission, the amount of energy released can be used to boil away 250,000 kilograms of water. So imagine if you allow 1 kilogram of uranium all of a sudden to undergo fission, how much energy is released. That is a bomb, isn't it? Well, we will discuss that as we go on. So at the moment, let's see what a chain reaction is. What is a chain reaction? Well, here I have explained what chain reaction is. Now, this is the first uranium nucleus absorbs a slow neutron or the thermal neutron, undergoes fission, produces fission products, and that fission product include 2 free neutrons. Well, if this is barium and this is krypton, 2 free neutrons are represented by these black dots. So a uranium nucleus absorbs a thermal neutron, undergoes fission, producing nucleus of barium, nucleus of krypton, and free neutrons, of course, a lot of energy. And each of these neutrons now can go and produce further fission in, say, at least 2 other nuclei, producing barium, krypton, 2 neutrons, barium, krypton, 2 neutrons, and these 2 neutrons in turn will produce fission in 4 different nuclei. And the neutrons released there will create fission in 8 different nuclei. You see how that spreads as a chain. Now, this is what is called the chain reaction in nuclear energy. So in a mass of uranium-235, if one nucleus undergoes fission, the neutrons that are released in this fission can cause fission in 3 or 2, depending on the number of free neutrons, different nuclei, releasing more neutrons. The generation of neutrons can produce 27 different fissions as we go on, and 81, and so on. So each of these neutrons, watch an animation of that chain reaction. Now what you see here is within a fraction of a second, the whole mass of uranium can undergo fission. Look at that. It doesn't take a very long time. So each of the neutron produce fission, further fission in other uranium-235 nucleus, releasing more neutrons, more fission, more neutrons, more fission, and it spreads right through the material within a very short time. Now, such a chain reaction is called an uncontrolled chain reaction. Well, an uncontrolled chain reaction is what we use in the construction of a bomb. But if you want to harness nuclear energy and use it for producing electricity or any other peaceful purposes, then we cannot allow this uncontrolled reaction to take place. We must control it by some means. We will talk about that briefly as we move on. Okay. Well, that brings us to the next concept of what is called critical mass. Can the chain reaction occur in any amount of uranium? Suppose I have this much of uranium. Can a chain reaction be sustained in a small mass like this? Well, that's an important factor. In order that a chain reaction may be sustained within a given mass of fissionable material, at least 1 neutron per fission should be available to produce further fission. Now, if those neutrons are allowed to escape, suppose you have a material, say like this. 1 nucleus absorbs a neutron and it undergoes fission, producing, let us say, 2 neutrons. Now, if those 2 neutrons, these neutrons are very fast actually when they come out of the nucleus. They're very fast, they carry very large amount of energy. That means they can escape the mass of the material pretty fast. If they escape before they can be caught by other nuclei, that means a chain reaction cannot sustain in a mass like this. So in order that a chain reaction may be sustained, at least one neutron produced in one fission should be available to produce further fission in other nuclei. Then only you can sustain it. Now, neutrons produced in fission are fast moving, and there is a good chance that they escape before being captured for further fission. If the mass of the fissionable material is too small, the neutrons have a greater chance to escape. That means a chain reaction cannot be sustained in a small mass like that. That means in order to sustain a chain reaction, you need a minimum mass. A minimum mass that is necessary to start and sustain a chain reaction is called the critical mass of that fissionable material. So each fissionable material has a critical mass, which is the minimum amount of material that will start and sustain a chain reaction. So if you have a small amount of fissionable material which is below critical mass, it is not a very harmful object. It does not, well, it will not explode into a bomb. So a bomb, in order to make a bomb, you need a certain amount of fissionable material above critical mass. Well, that is probably one of the technical details of constructing a bomb. The effective neutron multiplication factor K, an important factor. What is the meaning of neutron multiplication factor? Well, each fission releases an average of 2 neutrons, let us say 2 or 3, it doesn't really matter. So we will talk about the effective neutron multiplication factor K. What is that? It's the average number of neutrons from one fission that are available to cause further fission in other nuclei. The value of K determines how a nuclear chain reaction proceeds. Can a chain reaction proceed, or will a chain reaction sort of die down? Depends on the value of K. Now what happens if K is less than 1? K is less than 1 means it is subcritical. That means less than 1 neutron per fission is available for further fission. You see, in order to sustain a steady level for each fission, at least 1 neutron should go and produce further fission. Then only you will have a sustained chain reaction. If K is less than 1, that refers to subcritical mass, and a chain reaction cannot be sustained. If K equal to 1, well, that is the critical mass, K equal to 1. That means for every fission, at least 1 neutron will be available to produce next fission. That means the chain reaction can be allowed to proceed at a constant rate, and that's very useful. On the other hand, if K greater than 1, it will be supercritical mass. That means when a chain reaction starts, for each fission there will be more than 1 neutrons made available for further fission. That means the chain reaction will go and proceed in almost an uncontrollable manner, and that K greater than 1 will result in an uncontrollable chain reaction. K equal to 1 will result in a controlled chain reaction. K less than 1 will result in the chain reaction dying down, and there will be no result. And that brings us to the concept of the fission bomb. How do you construct a bomb? Alright, don't go and start making bombs. Well, you cannot. If people could make bombs easily, then this world would have come to an end long time ago. Is that right? Because there are a lot of people who want to destroy a lot of others. Our civilization I think it is the instinct of every animal. Is that right? The instinct to kill one another. Am I right? I was hoping when I was a child in the elementary school, when those days when I used to read about wars and hatred and things like that, I used to think that as time goes on, people will get more and more matured, educated, and will become better. And the world will be a better place to live, a peaceful place to live. But are we in a better place now, about 50, 55 years after I had that dream? Not really. People want to destroy each other. Selfishness is part of every human being, for that matter, in every living creature. Selfishness. So, atom bomb, if somebody can make a fission bomb, well, I don't think our civilization will last. And so, the bombs that are at the moment are in the custody of governments, and it has to be kept in a very, well, it has to be kept so that others, terrorists will not get their hands on it. It's very important. Now, I will not go into the details of producing an atom bomb, a fission bomb, but by our discussion you know that in order to produce a fission bomb, you need a supercritical mass of fissionable material. Now, if you keep a supercritical mass, suppose this is a supercritical mass of uranium-235, I will not be able to hold it. I will not be able to survive, because this will explode spontaneously in a fraction of a second. So, you cannot really make a fission bomb and carry it with you. Well, you need to assemble it just before it is going to be released. That is, the assembly of the bomb should take place after it is being released. Otherwise, you're going to be killed by it. So how are you going to do that? Uncontrolled chain reaction in a lump of uranium-235 greater than its critical mass is an atom bomb. Now, in the construction of such a bomb, two pieces of uranium-235 are both below critical mass and kept separated from each other. Well, that is the trick of making and carrying a bomb. Well, if this is a lump of uranium of subcritical mass, safe for me to hold, and this is another lump of uranium of subcritical mass. Now, if I can by somehow make these pieces into one piece, well, that again is not very simple. I need to move these in such a way and violently sort of, well, I need to create that kind of a big collision so that the two subcritical mass become a supercritical mass. So that is the bomb. Well, how is it done? Well, America was the first country which did that. And the bomb that was dropped in Hiroshima was a bomb like this. Now, what is done is, we have a detonator. Well, the sound you heard is one of the uranium pieces falling down. But fortunately, it is still subcritical. We have a detonator which will fire a subcritical mass of uranium into another piece of uranium-235, again subcritical. And this will be fired at a very high energy so that the two will become a single piece, and then it will be supercritical. And that's a bomb. And this process is done after the bomb has been dropped. You cannot do it before dropping it, because you need to look after your own life. So the device is safe as long as the two pieces are separated. In order to make a bomb, the detonator will fire one piece into the other so that the total mass exceeds the critical mass. Then you have a bomb. Well, we have made the bomb, have we? Well, don't even think about it. Just let's not think about destruction. Let's think about construction now. How can we use nuclear energy in a constructive way, in a peaceful way? Well, it is being used in a peaceful way in many parts of the world. The construction of a nuclear reactor. So a nuclear reactor is a device in which chain reaction is allowed to proceed at a controlled manner so that we can harness the energy of fission and use it to produce electricity. Well, there are snacks in it, there are merits in it, and those kind of things are debated these days. If you follow the politics of energy, I'm sure you understand a lot of it. To maintain a sustained, controlled reaction for every 2 or 3 neutrons that release per fission, one must be allowed to proceed to do further fission. Not more, not less. If it is more, it becomes supercritical. If it is less, it becomes subcritical. So, if this is a nucleus of uranium that undergoes fission, if there are 2 neutrons produced, one must be taken away, removed, and only one must be allowed to proceed further. And again here, fission, free neutrons, one must be removed, and only one should be allowed to proceed. That means there must be some kind of an effective control system to control the rate of fission. The rate of fission cannot accelerate. It cannot decelerate. It has to be maintained at a constant rate. If the ratio is less than 1, well, the ratio of neutrons available for further fission is less than 1, the reaction will die down. If it is more than 1, it becomes a bomb. If you make a reactor and it becomes a bomb, well, then we failed in our purpose. Nuclear reactions can be controlled by using neutron-absorbing materials. Now, boron is a good example of neutron-absorbing material. So, in a nuclear reactor, you have control rods which are made of boron, which will absorb extra neutrons, and only 1 neutron per fission is allowed to produce further fission. So a nuclear reactor is a device in which chain reaction is initiated, controlled, and sustained at a steady rate. Now, here is a sequence of what happens there. If you have 1 uranium-235 undergoing fission by absorbing a slow neutron, it produces barium, krypton, and say 3 neutrons. Now, out of the 3, there is a material called moderator. Now, we will talk about that as we go on. A reactor contains a material called moderator. Moderator, the purpose of the moderator is to slow down the neutrons, because fission is produced by the absorption of slow neutrons by the uranium nuclei. So these neutrons, when they hit against the molecules or nuclei of the atoms of this moderator, they slow down. And now, a number of these need to be removed by what are called control rods. So control rods are used to remove the extra neutrons, and only the fission is allowed to proceed at a controlled rate. All right. What are the major components of a nuclear reactor? Now, of course, fuel. What is the fuel used in a nuclear reactor? Now, the fuel used in a nuclear reactor is pellets of uranium oxide, UO2. And they are arranged in tubes to form the fuel rods. So, nucleum oxide in steel rods form what are called fuel rods. The rods are arranged into fuel assemblies in the reaction core at the center. I'll show you a diagram as we go on. Now, the second important part of a reactor is the moderator. And I mentioned what a moderator is in about a couple of minutes ago. A moderator is a material that is used to slow down neutrons. If neutrons produced in a fission are not slowed down, they will simply escape from the body of the reactor. They need to be slowed down, and the slowing down is done by repeated collision of these neutrons with the nuclei of some materials. Well, heavy water is a good example of a moderator. Some reactors use graphite. The carbon nuclei are very effective in slowing down neutrons. So graphite is a good moderator, and heavy water is another good moderator. That means heavy water is actually an important ingredient in making reactors. And reactor is an important ingredient in producing actually fissionable material. And that's the reason why during the Second World War, Germany was feverishly working with reactors. And they needed a lot of heavy water. What is heavy water? Well, normal water is H2O. Heavy water, instead of the normal hydrogen, you have the isotope of hydrogen, which is deuterium. That is one proton and one neutron. That is deuterium. So the water made of a combination of deuterium and oxygen is heavy water. And the heavy water is very effective in slowing down neutrons. Now, Hitler was constructing a heavy water plant, and one of the aims of the Allied troop was to go and destroy it. Actually, there is a movie which shows clearly the plan and how they executed the destruction of the heavy water plant that Hitler was building somewhere in Europe. So, moderator is the electron to slow down neutrons. Now, control rods, we again talked about it. Control rods are controlling devices, materials that can absorb neutrons so that the chain reaction can be allowed to proceed at a controlled rate. And most commonly used material is cadmium, hafnium, or boron. They are all effective nuclear absorbers. Another important part of a nuclear reactor is coolant. You know that nuclear reactions, the nuclear fission, will generate large amount of energy. And that energy, most of it will appear in the form of heat. If that extra heat is not removed, the nuclear reactor will melt down. And a meltdown will cause almost like the explosion of an atom bomb. A lot of radioactive materials will be released. So a meltdown in a nuclear reactor cannot happen. You need to effectively remove the heat produced during fission. So these are the important parts of a nuclear reactor. And you can see I have illustrated that in here. Now, these are the fuel rod. This is the complete reactor body. And this is the core of the reactor. They are the fuel rods, uranium oxide. And it is inside a steel chamber. And you have control rods. And the moderator is actually water, heavy water. Now, coolant. Water also is used as the coolant. That means this water being circulated will remove heat and give it out to the water that is circulating here. That means this heat from the core of the reactor can be extracted by this water, which when circulated through this tube will heat up the water in here, which will produce steam, and the steam will then drive the turbines, which will then produce electricity. And this water can be recycled and can be pumped back. Well, that is in a sense what a reactor is. So heat is produced in a nuclear reactor when neutrons strike uranium atoms, causing them to fission in a continuous controlled chain reaction. Neutron absorbers are placed among the fuel rods for achieving that controlling process. When the control rods are pulled out, you can actually shut down the reactor by pulling out the control rods. You can start the reactor by inserting the control rods. Now, when they are inserted into the core, more neutrons are absorbed and the chain reaction, well, the chain reaction can be stopped or allowed to control in a controlled manner. Most commercial reactors use ordinary water to remove the heat. Now, if you want the two jobs to be done by water, that is the job of a moderator and that of a coolant, then you have to use heavy water. Now, such reactors are sometimes called the swimming pool type because the whole process, the whole reactor is built inside water. Well, in a PWR, that is pressurized water reactor. This is a pressurized water reactor. The heat is removed from the reactor by water flowing in this pressurized chamber. This purple color is the pressurized water chamber that removes the heat and then transfers it into the secondary water circulating. The secondary water circulating system will absorb the heat, will generate steam, which is then used for producing electricity. So the heat is transferred to a second water loop through a heat exchanger. This is the heat exchanger. Alright. Water boils in the heat exchanger, producing steam at very high pressure, which then turns the turbine, producing electricity. Well, in a BWR, BWR stands for boiling water reactor. Now, it's a much more simplified one. There is no heat exchanger. The coolant itself, or the moderator and coolant itself, will be the heat exchanger. In other words, the heat is generated directly there. Instead of using a heat exchanger, heat is generated directly inside the chamber itself. And that steam is then used for generating electricity. So that is a boiling water reactor. Now, what is a breeder reactor? Of course, breeder means something that breeds. Breeds what? Well, a reactor uses fissionable material as the fuel. If it is called a breeder reactor, probably it means it breeds more fissionable material. So a breeder reactor will produce more fissionable material. Well, how can that be done? Under appropriate operating conditions, the neutrons given off by fission reaction can breed more fuel from otherwise non-fissionable isotopes. Well, I told you that most of the uranium that is available naturally is non-fissionable uranium-238. And remember, the fuel that is used in the nuclear reactor is not pure fissionable material. It is enriched uranium. That means if naturally occurring uranium contains, say, 0.1% of the fissionable material uranium-235, enriched uranium will contain about 15% of uranium-235. The rest are all non-fissionable uranium-238. So when you look at a fuel rod, most of the fuel rod is non-fissionable uranium-238. Only a small part of it is fissionable U-235. Now, in a breeder reactor, you can actually make that uranium-238, which is otherwise non-fissionable, into fissionable material by making it radioactive. Now, how is that possible? You know that when a radioactive nucleus emits a beta radiation, the atomic number increases by 1 unit. That's right. So, if uranium-92 can be made to emit a beta, it will become an element of atomic number 93. Now, if that again emits a beta, it can produce an element of atomic number 94, and that is plutonium. And plutonium is a readily fissionable material. Now, this is how it happens. Uranium-92-238, a non-fissionable isotope of uranium, absorbs a neutron, becomes uranium-239. And uranium-239 emits a beta. What happens? Uranium-239 emits a beta. What is the resulting element? The resulting element will have one atomic number 1 unit greater and the same mass number. What is the element that is 1 unit higher than uranium? It is neptunium. So it's neptunium-93-239. Now, this neptunium-93-239 is again beta active. It will emit a beta radiation. The result is an element 1 unit higher than neptunium, which will be plutonium-94-239. Now, this is the process. So when you have a fuel rod that contains large quantities of this non-fissionable material, now they will be absorbing neutrons and undergoing this degeneration, producing plutonium in there. That means you are actually producing more fissionable material. That is a breeder reactor. So the most common breeding reaction is that of plutonium-239 from the non-fissionable uranium-238. As I explained, uranium-238 absorbs neutron and becomes beta active. It emits 2 successive beta particles and become a nucleus of plutonium, a very readily fissionable materials. Now, the reactor core consists of thousands of stainless steel tubes containing a mixture of uranium and plutonium oxides, about 15 to 20% fissionable plutonium-239. Surrounding the core is a region called the breeder blanket, consisting of tubes filled only with uranium oxide. Now, such a reactor can produce about 20% more fuel than it consumes by the breeding reaction. Now, why is the big controversy about the uranium reprocessing by Iran? Well, when you reprocess the spent fuel, when you take out the fuel rod that has been used, remember that contains large amounts of plutonium, which is readily fissionable. Now, a reprocessing plant is a place where you take these spent fuels and remove that fissionable plutonium from it. And if you can do that systematically, you can build large amounts of fissionable material. So, when a country builds reprocessing plant, there's only one thing that can come to your mind. Why are they doing it? They are building stockpiles of large quantities of fissionable materials. Why? The only intention will be to produce bombs. So, if Iran is having a nuclear reprocessing plant built, recently there was mention of a secret reprocessing plant that has been discovered. And now there is talks that Iran, instead of using their reprocessing plant, they will send these materials into Russia to reprocess so that they will produce these materials which can be then used for medical purposes and not for making bombs. Well, I hope some of you at least are following some of these processes that are taking place in the world in the realm of nuclear energy. Now, it's very important because the survival of mankind itself will depend on how closely we can keep this without getting into the hands of terrorists and other organizations. Well, that's an animation of actually what happens. Uranium-238 becomes uranium-239, emits a beta and becomes neptunium-239. It will emit a beta and finally becomes plutonium-239. So watch that carefully one more time. Uranium-238 becomes uranium-239. Emits a beta, becomes neptunium-239. Emits a beta, becomes plutonium-239. All right. I think that sort of explains itself. Well, that's about what we need to know about nuclear fission. And before I close this lesson, let me spend a couple of minutes talking about nuclear fusion. Well, nuclear fusion is still not a means of producing nuclear energy yet, and therefore we will not be spending a lot of time on it. Nuclear fusion is the energy producing process which takes place continuously in the sun and in the stars. You see, in the formation of a star, if you know the history of the formation of birth of a star, now how does a star take birth? The nebula, the space between stars and galaxies, are filled with all kinds of gaseous particles. Any disturbance anywhere, any part of the universe, like a supernova for example, can create an instability. And that instability will bring these particles together by force of gravity. And eventually, after millions of years, the gravity pulls all these particles together, creating great pressure and temperature. A stage will come when the pressure and temperature inside is so tremendous that this gas inside is no longer the normal form, but they are plasma. The electrons are stripped off the atoms, and these nuclei, well, mainly hydrogen, the nuclei will be traveling with tremendous speed, and they hit against each other and fuse to become deuterium, and then deuterium and deuterium will fuse to become helium. So this is the process of a star formation. But in order for this to happen, the temperature must be of the order of about 15 million degrees Celsius. Now, temperatures below that cannot start a nuclear fusion. In the core of the sun, at temperatures of 10 to 15 million degrees Celsius, hydrogen is converted to helium, providing enough energy to sustain the life on Earth. In fact, all that energy that we get from the sun is the byproduct of this nuclear fusion. So fusion can produce tremendous amount of energy. So this is what happens. A deuterium fusing with a tritium produces a helium nucleus, a neutron, and tremendous amount of energy. So what are the required materials to start a fusion reaction? You need deuterium and tritium. Well, deuterium is a proton and a neutron. Tritium is a proton and 2 neutrons. Combined, you have a nucleus of helium, 2 protons and 2 neutrons, and of course a free neutron comes out of it. Now, most suitable reaction occurs between nuclei of these deuterium and tritium. Now, at the temperatures required for deuterium-tritium fusion, over 15 million degrees Celsius, the fuel has actually changed from gas. The hydrogen has changed from the gaseous state into the plasma state. And in the plasma state, actually the electrons are stripped off. And in order to produce nuclear fusion, we need to create that kind of a temperature on the surface of the Earth. Now, is that possible? Well, there is possibility. If you want to create a fusion bomb, a hydrogen bomb, the trigger for that will be a fission bomb. So a fission bomb exploding will create the necessary temperature condition to activate fusion. And that's the reason why a hydrogen bomb, in fact, America has a stockpile of large number of these hydrogen bombs where fusion energy is used to produce large amounts of energy. And the trigger of that is a fission bomb to create that kind of energy. In order to use that in a reactor, it is not possible. It's not a feasible thing. And that is why we are unable to use or harness the fusion energy for producing reaction. Now, seawater contains an abundance of deuterium. And tritium is part of it's rather difficult to find tritium. So if you want to produce nuclear fusion, the required fuel will be deuterium and tritium. Deuterium can be found abundantly in seawater, but tritium cannot be found as much. Now, there is no sizable natural source since tritium is radioactive with a half-life of about 10 years. Now, it can be obtained by breeding the tritium from lithium. It is possible to create that. Now, some advantages of fusion reaction are, what are some of the advantages? It's a vast new source of energy. The energy released in fusion is much, much greater than energy released in fission. So it's a very big source of energy if we can harness it. Now, no atmospheric pollution leading to acid rain or greenhouse effect. You see, in the case of a fusion bomb, the damage done by a fusion bomb is not only the tremendous amount of energy released at the time of explosion, but a fission bomb will be harmful for many, many decades to come, because the products of fission are very radioactive, and everything that is surrounding the region will become radioactive. That means if in a region where a fission bomb has been exploded, that region will not be safe for 50 or 100 years because of the presence of that radiation. So a fission bomb is a very dirty bomb. In addition to killing and destroying at the present time, it will keep on killing for many, many years to come due to that destroying radiations of the radioactive materials that are generated during that time. Whereas a fusion bomb, it can be produced, will be a clean bomb. The products will not be radioactive. And also, it doesn't produce any greenhouse gases or things like that. There is no waste disposal problems. One of the major problems with fission energy is that the products of fission are very highly radioactive. So the fuel rods that are in a reactor once those fuel rods are being used and exhausted, you need to remove them. Now, removing them and storing is one of the greatest problems of using nuclear energy, because those materials are very highly radioactive. Where are we going to store them? Now, will you be happy if those materials are stored in your backyard? Well, there are places in the United States where hundreds of millions of tons of these radioactive waste materials are stored. Well, some of them in the mountainous regions of Nevada. Well, that means if you go near there, well, not quite, because they're all very safely contained within very safe containers. So, one of the reasons why nuclear energy is still not a feasible form of energy to solve our energy needs in a large scale is the problem of disposing of the waste materials produced in fission. If fusion can be harnessed, if we can find a way to use fusion energy in a controlled manner, then those problems can be solved. Waste disposal problems are much more minimized in fusion reactions. Well, all these are very important when we consider fusion in place of fission. Well, all these are left for later generations to tackle and see how much we can do with these. Can we produce energy from fusion? And can we solve all our energy problems? Can we solve the greenhouse effect problems? Can we solve the environmental pollution problems? Well, that is all problems that we pass on from generation to generation. It's a challenge for all of you. And I hope I gave you some food for thought about not only the challenges of nuclear energy, but also the perils of nuclear energy. Well, I hope you enjoyed this lesson and enjoyed this course. Well, if you have any questions, please get back to me anytime, and I'll be glad to respond to your questions.